lab 6.2 called the Decomposition of Water. And before we get it started, there's a few things that we should discuss, or I should explain, just so you kind of understand what you're looking at here. First of all, let's think about the title of the lab. The title of the lab is the Decomposition of Water. So it's very important that we understand what we mean when we say decomposition, so that you kind of have some insight into what this lab is going to be all about. So the word decomposition means to break apart. So in this lab, what we're going to be doing is taking a sample of water and decomposing it, or breaking it apart into its individual components. One of the things that's useful with this lab is that we already know that water, the chemical symbol or the chemical formula for water is H2O. That's something that most kids come to class already knowing, so we can call that background knowledge. So when we think about decomposing water and breaking it apart into its individual components, we're thinking about breaking apart the hydrogen from the oxygen and separating them into their individual elements. So that's what we're going to be doing in this lab. Now, it's important to think back to Chapter 5 real quick, because Chapter 5 was all about separating mixtures of things. And the very last section, or close to the last section in Chapter 5, talked about how we can determine if something is a mixture or a pure substance. And the gist of it was, if we applied all of those different separation techniques to a sample of something unknown, and that sample did not break down into anything at all, and it just stayed the same no matter what we did to try and separate it, then we could basically say it was a pure substance. So we came up with the idea that water must be a pure substance, because water is not something that we can separate based on any of those methods from Chapter 5. So water is definitely not a mixture. It's definitely a pure substance, even though it's made up of two things. It's made up of hydrogen and oxygen. The difference between a mixture and a compound that's a pure substance is that in something like water, which is a compound, it's made up of two parts, but those parts are chemically connected to each other. They're chemically bonded to each other. Where in a mixture, for example, if I put salt and water together, the salt and the water will mix, and the salt will dissolve and spread out throughout the water, but the salt and the water never chemically combine with each other. So therefore that's a mixture, and that's kind of how you can tell the difference. So when we have something like water and we want to break it apart, we can't do that using any physical means like we did in Chapter 5. We can't filter it. We can't fractionally distill it. There's nothing we can do physically to separate the hydrogen from the oxygen. So what we have to do then is to chemically separate it by means of a chemical reaction. So what we're going to be doing in this lab is a method called electrolysis. Now, at the end of the day, the process itself is not what we're trying to get at. That's not our end goal. The end goal in this particular lab is to figure out, when I take water and I decompose it, or break it apart into its individual elements, how much of that water is hydrogen and how much of that water is oxygen. So we're going to be looking at ratios. We're going to be looking to figure out the volume ratio of hydrogen to oxygen and the mass ratio of hydrogen to oxygen in a sample of water. So we're going to take the water, we're going to separate it into hydrogen and oxygen, and then we're going to measure it. And we're going to say, well, how much of the water was hydrogen and how much was oxygen? And we're going to be able to compare the volume and the mass ratios of hydrogen to oxygen. So that's the end goal here. But in order to get there, it's probably worth understanding the process at least a little bit. So let's take a look at what we have here. Right here we have, this is a bucket of water, and I'll try to move this so you guys can see. There's water inside that bucket. And then we have these two test tubes right here that are turned upside down. And what you can't tell just yet is that there is water filling those test tubes. So those test tubes are full of water with the mouth of the test tube underneath the surface level of the water in the bucket, so that the water and the test tubes can't spill out. Then we have these two things called electrodes. These little, they're like a little black J hooks, right? So let me show you what they look like when they're not attached to the setup, just so it kind of makes some sense for you. This is just a regular electrode. Let's see if I can hold this back here for you to see a little bit better. Or maybe not. Maybe it's better here. Okay, there you go. So there's an electrode. So what we've done is I basically just took a little binder clip, and this clamp that's holding the test tube in place has a little arm that's kind of sticking out. So I took the binder clip and I just clipped the electrode to the clamp that's holding the test tube in place. Now what's important is that this part of the electrode, the end of it, is directly under the mouth of the test tube. So it's kind of like this. Let me show you outside the water. Here's the test tube, and then the end of the electrode is just below the level of the test tube, but it's directly underneath the opening of the test tube. So it has to be like this. If the electrode were out here, then this process wouldn't work. The electrode has to be to where the end of the electrode is directly under the mouth of the test tube like this. And so that's how we have it set up in this little bucket of water. So let me see if you can tell a little bit better now that I've explained kind of what's happening. So there's 2 electrodes, one for each test tube, and the very tip of the electrode is directly under the opening of the test tube. And I wonder if it would help to have a little bit of light. Sometimes the light creates a really bad glare that makes it hard to see these when we have clear test tubes and clear water. So let me see if I can get a light on real quick and if that'll make a difference. I Oh, for heaven's sakes. Let me see if I can just turn it on here. It's always something, isn't it? Every time I try to do a video, this little thing doesn't want to work. Let me try it on here. Oh, I must not be able to do that while I'm recording. Okay, never mind. I can't change the lighting once I start recording, so we'll just leave it as it is. Okay, so we have 2 test tubes full of water, the bucket with some water. We've got 2 electrodes with the end directly underneath the mouth of each of the 2 test tubes. Then what we have is we've got a red cord and a black cord, and they're little alligator clips that are attached to the top of each of the electrodes. I don't know if you can see that in there like that. So there's one clip on that electrode, and there's one there. Okay, they kind of look like jumper cables if you've ever seen that. And then the other end is hooked up over here. So we have the red cord is running a positive charge, and the black cord is running a negative charge. So what happens is, from the battery, when I turn it on in a minute, the positive charge will run through the red cord, the negative through the black cord, over here to the electrodes that they're attached to. So the red cord, which has the positive charge will run through the electrode and to the very end of the electrode that's exposed in the water. I don't know if you can see that very well. It's kind of dark. I'm trying to adjust it there. That might be a little bit better. So the tip of the electrode, which looks like I showed you guys a minute ago, looks like this. So that positive charge is going to run through and come out right here at the end of that electrode. Then the black one's running a negative charge, and so the end of its electrode will be generating a negative charge. And so what's going to happen is, between the two, the circuit will be closed from the battery through the cords into the electrodes through the water. And that's basically the circuit where the electricity will be passing through. Keeping in mind it is a low voltage amount of electricity, so it's not harmful to anyone. So once we turn on the battery in a second, we're going to pass a little bit of electricity through the water, and then what's going to happen is it's going to break apart the hydrogen and the oxygen. Now, here's how this method works. Actually, I'm going to turn it on so you can start to see the process. So what you're seeing now is the gas that's being generated. So here's what's happening. As the electrical current is being passed through the water, the black cord and then the electrode attached to the black cord is generating a negative charge. So as the hydrogen and oxygen break apart from each other, one of those elements is going to be positively charged and therefore attracted to the negatively charged electrode, which is attached to the black cord. So whichever of the elements is positively charged is going to be attracted to this side right here, because this black cord has a negative charge and opposite charges attract. Now, this cord over here, the red one, is generating a positive charge. So the element that is negatively charged is going to be attracted to that positively charged electrode, and therefore generating this gas. So what happens is, once the hydrogen and oxygen break apart, they are attracted to their respective electrodes, and once they kind of are attracted to the electrode, they kind of basically like run over to the electrode and turn into their gas state. And because gases are less dense than water, those gases will rise, which is why we have to have the test tube directly above the electrode. So as the gases are rising off of the electrode, the gases are being collected in the test tube. So a couple things to consider here. It's very interesting that when hydrogen and oxygen are bonded together, when it's H2O and it forms water, at room temperature, H2O is a liquid. As soon as we break apart the hydrogens from the oxygens, the hydrogen and the oxygen at room temperature, when they're alone and unbonded to anything else, are gases. So we take the hydrogen and oxygen bonded together in its liquid state as water, and when they break apart, they turn into gases. It's really kind of fascinating. So that's what you're observing here, is the collection of the gases. So one of the gases, the one that is positively charged, is being collected in the test tube on the right, and the one that's negatively charged is being collected in the test tube on the left. That's how we separate them, by generating opposite charges. So when they break apart and they're oppositely charged ions, they go to their respective electrodes, and they essentially separate themselves that way. And because the electrode is placed directly under the mouth of the test tube, when it's attracted to that electrode and then turns into a gas, it will rise and be collected in the test tube. So that is what you're observing. Now, the reason that, let's see if we can see what's going on here. Okay, if you look at the top of the test tube, you can see that this test tube has already collected probably twice the amount of gas as this test tube. Because at the beginning they were both completely full of water, and as the gas rises up to the top, it's going to push the water out. So this empty, what appears to be empty space at the top, is actually a gas that's being collected. So this gas, whichever one it might be, is being collected in twice the amount of this gas. Now the reason this one looks white instead of clear like this one is because this one is generating a lot more gas, which makes sense because there's a lot more gas being collected in the test tube. And even as I'm speaking, you can see the water level falling pretty rapidly, especially if you pay attention to the little dots behind it and you kind of have a reference point. You can see that it's dropping at a pretty good pace. The one on this side, while it is collecting gas, it's not collecting it quite at the same rate as the one on the right-hand side. And if you look at the electrodes, you can see the gas coming off this one really fast. You can see the gas coming off this one too, just not nearly at the same, at the same pace. Okay, so one more thing that I wanted to talk to you guys about in terms of how this is set up and what's going on is, in this particular lab, we use something called a catalyst. And this is definitely something that will come up when you guys get to your semester exam. So it's important to talk about it. This reaction all by itself would work just fine. So if we set all this up just as you see it and we ran the experiment, we would be able to separate the hydrogen from the oxygen. The only thing is it would happen really, really slow. So you wouldn't see this really impressive amount of gas being produced in this electrode, that just has gas pouring off of it. You wouldn't see that. You would see it bubbles, but it would be much slower. So what we did before we even started this lab is we added some baking soda, like this. We added a few scoops of baking soda to the water. So it's important for you to understand the purpose of the baking soda. The baking soda has absolutely nothing to do with the outcome of the lab. We are still separating water into hydrogen and oxygen. And the end result and the ratios that we come up with will be the same no matter what. So the purpose of the baking soda then is just to make this reaction go a little bit faster. First of all, it's more impressive when it goes faster. And second of all, in this class we're always limited with time. So the faster we can get something done, the better. So baking soda is what we call, in this case, we use it as a catalyst. And that's spelled C-A-T-A-L-Y-S-T, catalyst. And a catalyst is something that you add to a chemical reaction in order to make the chemical reaction go faster. A catalyst will not affect the outcome at all. It will only get us to the outcome a little bit faster. So it's kind of like when you're in PE class and you have to do the mile. You can walk it and it'll take forever, or you can run it and get it done faster. At the end of the day, you still did your mile, but if you walked it, it took a long time. If you ran it, you got there faster. So that's what a catalyst is. It just gets you to your end result a little bit faster. And it's something that speeds up the rate of a chemical reaction. So it's important for you guys to know that that was part of our setup as well. Okay, so here's what we would do next. We would actually probably let this run a little bit longer, but for the sake of where we're at, I'm going to push the little off button here. No, I'll let it keep going. Here's what we would do. So normally I would hit the off button, and we would measure how much gas is produced. We would say, okay, we'd mark the level here, and we mark this level here, and we could pull the test tubes out, and we could fill this much space with water, and then measure how much space that is, and say that's how much gas was produced. Okay, so that's and that way, when we measure it that way, we'd be measuring the volume. So when we're looking at the test tubes, and we can state some things right off the bat. We can certainly tell that whichever gas was produced here has a greater volume than the gas that was produced here. And when we measure it, we would find, in fact, this test tube collects exactly twice the amount of gas as this test tube. And so that can lead us in the direction of trying to figure out which one of those gases is the hydrogen and which one is the oxygen. And we'll come back to that in just a second. One of the other things that we would normally do in this lab, we did not do this in class either, but it's important to talk about just in terms of identifying the gases. What we could do is we could let this run a little bit longer, and then we could stopper the test tube and pull the test tube out, and then we could keep the test tube inverted and let the water out, the remaining water in the test tube out into the sink. The gases are pretty light, so the gases, as long as we held the test tube upside down, so the mouth was down, both the hydrogen and the oxygen would stay in the test tube. And then what we could do is we could use a splint, which is basically like a popsicle stick. We could light it on fire, and if we put the lit, basically popsicle stick, underneath the mouth of the test tube containing hydrogen, it would pop. It would make a popping sound. And so we could do that to identify which one was hydrogen. And then if we took something similar, like a popsicle stick that was on fire but that we blow it out, but where it's glowing a little bit, we call it a glowing splint. If we took a glowing splint and we put it inside the test tube with the oxygen, it would reignite itself, which is pretty impressive too. So we could use that particular test. We'd be testing the flammability of the two gases to identify the two gases. Flammability is a characteristic property. It can help us to distinguish between things. So at this point in the lab, because we can't really tell conclusively which one is hydrogen and which one's oxygen, although we can tell based on using our logic, but if we wanted to find out conclusively, we could see how they react, how their flammabilities differ from each other. And then we could say certainly one of them is hydrogen and certainly one of them is oxygen. In this case, I'm just going to cut to the chase and tell you, because I know how this works, that the test tube on the right is the one that's collecting the hydrogen, and the test tube on the left is the one that's collecting the oxygen. So then we, again, like I said before, we would measure how much hydrogen was produced, we'd measure how much oxygen was produced, and we would compare those two. So this is where I stop the reaction, and we need to look at some numbers. So let's see if I can move this camera a little bit so that I can show you the whiteboard and how this all works out. Okie dokie. So really, the main thing at the end of all this is understanding the math behind it. So we said, so first of all, we're talking about water, H2O. The chemical formula for water already gives you some ideas about what the volume ratio probably could be, or what we could guess it to be. Because we know, especially if we looked at chemical bonds this week too, and we said, okay, there's an oxygen bonded to a hydrogen, bonded to another hydrogen. So we know in a molecule of water, we've got two hydrogens and we've got one oxygen. So when we measure the volumes that were found in the test tubes, we would find, and I'm going to write this out so you can see it, the volume ratio of hydrogen to oxygen is equal to 2 to 1. So when we say ratio of hydrogen to oxygen, hydrogen is the number that goes on the top, oxygen is the number that goes on the bottom. So this is the volume ratio. So again, if we were to look back over here at our test tubes, you can see that the test tube on the right has a much larger volume of gas than the test tube on the left. So the test tube on the right is hydrogen and the test tube on the left is oxygen. Okay, so hydrogen is created in double the amount, at least in terms of volume, double the quantity, double the volume of oxygen. So that's where we get our volume ratio, 2 to 1. So if we're, and again, let's also clarify the volume ratio of hydrogen to oxygen in water. Because there's many compounds that exist that contain hydrogen and oxygen. So when we talk about a ratio of hydrogen to oxygen, we always need to clarify what we're talking about, the hydrogen and the oxygen that we get when we decompose water. So again, we decompose some water, we collect the individual elements by themselves, and we find in a sample of water, the ratio of hydrogen to oxygen is 2 to 1, the volume ratio. And this is the easy one to remember because you can tell from the chemical formula, 2 hydrogens, 1 oxygen. Volume ratio, hydrogen to oxygen is 2 to 1. Now it's the mass ratio that will be a little bit confusing. So here's the thing with the mass ratio. What we're looking for is when I take apart water, when I decompose it and I gather the hydrogen and I gather the oxygen, what is the mass of the hydrogen that I collected when I decomposed water compared to the mass of the oxygen that I collected when I decomposed water? Now to do that, we can't measure the mass directly because in this case it would be very difficult. I'm not even sure what would be the beginning mass and ending mass and all that stuff if we tried to do it that way. So we're not going to measure the mass directly. We're going to use the density of hydrogen and multiply it times the volume. Remember, here's the volume up here. We already said it's 2 to 1. So the density of hydrogen times the volume of hydrogen over the density of oxygen times the volume of oxygen. Remember, we did this before when we did our little circle thing with density is mass equals mass over volume. If I want to solve for the mass, it's density times volume. Now you're probably like, well, where are you going to get the density from? Well, the good news is in our IPS book, it gives us the density on a nice little table on page 55. So you can look it up. And in terms of the volumes, we already did that. We already figured out the volume ratio is 2 to 1. So here's what we would do. We would look up the densities. If I'm remembering correctly, the density of hydrogen is 8.4 times 10 to the negative 5. Okay? And that, so the density times the volume. So here's our volume ratio again. Here's the volume of hydrogen compared to the volume of oxygen. So we'd say times 2, density times volume, divided by the same thing for oxygen. The density of oxygen is 3.6. What did I just said 3.6 when it's 1.3. No idea why I did that. 1.3 times 10 to the negative 3 times the volume, which is 1. And I know that I don't have to put times 1, but I want you to be able to see very clearly this 2 to 1 ratio here and the 2 to 1 ratio here for the volumes. So I wanted that to be obvious. Now, from a mathematical standpoint, I'm going to show you the way that I do this, and hopefully your math teachers won't hate me for it. But I can't, the calculators that we use in this class, we can't use scientific notation. We can't punch in a negative exponent like that in scientific notation. So here's what I do. When I see a number like this, I'm going to turn it back into its original decimal format, because then I can multiply that on the calculator. So in order to do that, here's how I do it. Here's my logic. I learned this a million years ago, and I've always used it because it's always worked. So I'm going to take 8.4, and I'm going to move the decimal to the left 5 times. So negative is moving in the negative direction 5 places. So we do this. Ready? 1, 2, 3, 4, 5. And all those little places right there are where zeros go. And the decimal goes here. So this number here is equal to 0.0000084. Okay? And that I'm going to now multiply times 2. We do the same thing with this number, 1.3, except we only have to move it to the left 3 times. Okay, so we go this. We do 1, 2, 3, and I put my little zeros and my decimal. So this number is the same as this. And then I'm going to multiply times 1. Even though I know I don't have to, but again, I just want you to be able to see that 2 to 1 volume ratio. Now, when we do this, we are going to get a really long number. It's like 0.12976, blah, 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 blah. So then we have to go back and apply our rules of significant digits. Remember, when we have all these zeros at the beginning of the number before a non-zero number, we don't count them as significant. So these zeros we're not going to count. So this has 2 significant digits, and this has 2 significant digits. So my answer should have 2 significant digits in the answer. So when I do all of this math, the mass ratio turns out to be 0.13. Here's what this means. In actuality, it's 0.13 over 1. And there's a reason I'm going to do it this way. If we go back to what we were looking at originally, when I take apart water and I break it up into hydrogen and oxygen, I want to know what's the mass of the hydrogen I created compared to the mass of the oxygen I created. Well, the mass of the hydrogen compared to the mass of the oxygen is 0.13 to 1, which means the mass of the hydrogen would be 0.13 compared to the mass of the oxygen, which is 1. What this means is that the oxygen is a lot heavier. Its mass is greater than the mass of the hydrogen, which if you go all the way back up here to the volume, but you're like, wait a second, we had twice as much hydrogen. How can that have less mass? Well, think about this. What if I had a sample of feathers and I had a sample of lead? And let's say that I had 100 cubic centimeters of feathers, but only 50 cubic centimeters of lead. So I had twice as much feathers in terms of its volume. Okay, so the volume of the feathers is 100 cubic centimeters, and the volume of the lead is 50. So from a volume standpoint, I have twice as much feathers. However, if I want to compare the masses of those two, well, it doesn't matter that I have twice as much feathers, because that lead is significantly heavier than those feathers, no doubt. So even though the volume ratio tells us there's twice as much hydrogen that's produced, that hydrogen is really light. It's really, really, really light compared to the mass of the oxygen. Hydrogens are the smallest elements that exist, by the way. And I don't know that hydrogens is the right way to say it, but a hydrogen atom is the smallest atom that exists. Oxygen's much bigger. So it kind of makes sense when you think about that the mass ratio would be so much smaller for hydrogen than oxygen. So again, this number right here tells us this. When I break apart water and I compare how much hydrogen to how much oxygen in terms of their masses, the mass of the hydrogen produced compared to the mass of the oxygen, this is your number. And that is super, super, super important. And I'm going to show you one other way to back this up. Or another thing I could say is another way to get to the same thing. Oh, one more thing before I forget. This formula right here is super important. You will see it again. Because you need to know, how did we do all of this? How do you get to the mass ratio? Because you can't measure that mass directly. We know the volume because that we can measure. And we know the density because we can look that up. So we can multiply the density times the volume for hydrogen, divide it by the density times the volume for oxygen, and get our mass ratio of hydrogen to oxygen. That you need to know no matter what. Please write it down if you're watching this and you weren't in class to do this. Okay, I'm going to show you one other way to get there. If we use what we've learned this past week based on the masses on the periodic table, okay, I'm going to draw a little line here. We know, if you look at the periodic table, that hydrogen has an atomic mass of 1. Oxygen has an atomic mass, I'll put AMU just so you can see it, AMU. Oxygen has an atomic mass of 16. Okay, this I'm getting directly from the periodic table. Now, if I want to figure out the mass ratio of hydrogen to oxygen in water, I can go, well, there's 2 hydrogens, so the mass of the hydrogen, right? So let me write it over here. So mass, if I can write, mass of hydrogen compared to the mass of oxygen, right? Just like we did up at the top up here, okay? Well, each hydrogen has an atomic mass of 1, and there's 2 of them. So the mass of the hydrogen is 2, because there's 2 of them in a molecule of water. The mass of this one oxygen, based on what the periodic table tells us, is 16. So we can do the mass ratio this way as well. Let me caution you, because you might want to look at that and go, oh, well, that's 8. No, it's not. 2 divided by 16 is not 8. 16 divided by 2 is 8. But 2 divided by 16 is not 8. When you type it into your calculator, you get 0.012. I'm sorry, that's not what you get. Goodness gracious, where's my brain today? You get 0.125, which, if you're using significant digits, will round to 0.13, which is the same thing we got up here. So there's 2 ways to get to the mass ratio. Let me black that out. There we go. There's 2 ways to get to the mass ratio of hydrogen to oxygen in a sample of water. We can do it this way using the density and volume, or we can do it this way using the periodic table and the atomic mass that's provided on the periodic table. This number you need to know for sure. That formula you need to know for sure. And then you also need to know the volume ratio of hydrogen to oxygen, which is 2 to 1. That's probably the easiest one for you to figure out. And that is the decomposition of water.